I'm going to do something a little bit different. So if you're new to my channel, if you joined after the warp drive video, welcome. Super happy to have you here. This is going to be a bit of a Q&A. Basically, what I realized is when I do these videos like once a month, which are deep dive explainers into some bit of physics from science fiction or into something that's just like a really confusing topic for people to get their heads around, there's a lot of questions. And honestly, answering questions and comments, like sometimes it's pretty easy to just do pretty quickly, but sometimes a lot of the people are asking the same questions. So I thought, hey, why not just like add a video that's just a bit more informal, a bit more relaxed, and is just a Q&A. So that's what I'm going to do. I've basically picked out 12 questions that I think either, came up a lot, or actually a few of them are just topics that I kind of thought myself, oh, hey, I didn't think about that before, and that might be interesting to chat about. So I'm going to go through each question in this video and just talk through it. I'd love to hear what you guys think, how you feel about each of the answers or some of the topics that I just think are cool things that we should talk about. And it's just a little bit of a add-in for the month while you're waiting for me to get to the next video, which I'll talk about later. So I'm going to break each one of these up, and I'll probably cut them into some shorts as well that I'll post in other places. So this is the first time I'm doing this, so if it's not as stylized, I do apologize. I'm not going to add in a bunch of graphics and stuff. If I feel like I need to do something to kind of explain a little bit more, then maybe I will. But I really need this to be just a more relaxed kind of chat about this type of stuff, rather than the level of like stylization I'm trying to do in the other videos or the main long videos. So this will be more chatty and less hardcore physics, but I will stop talking and get into it. Oh, I should also introduce myself as well, because, if you've just seen me from the warp video or maybe from some shorts, my name is Abby. I am a physicist. I'm currently in the write-up phase of my thesis. I do atomic and laser physics at the University of Oxford, and I work specifically in an area called plasma acceleration. So yeah, that's what I do, and I just think I learn a lot of stuff, but also I like to nerd out about a lot of stuff, and it's really cool to share that with you guys. So welcome, and let's do some Q&As. Starting with the very first question, which is, does time dilation make warp drive unnecessary? And the answer is no. A lot of people were a bit perturbed about how I spoke about Einstein's theory of special relativity and time dilation. Now, I think the main argument was that people maybe slightly misconstrued what I was saying about it and thought that I was saying that warp is acceleration to the speed of light. That's not what I was saying. The reason I brought that up is because when we look at what we actually know around us and how we interact with the world, we know that in order for us to travel places, we have to move at a speed. And if we want to increase that speed, we have to have acceleration. In order to do that, you have to put in energy. And what Einstein's theory of special relativity tells us is that there is no amount of energy that we can put into a system that will allow us to travel at the speed of light. It's just not possible for us to accelerate to that speed. So we have a limit as to how fast we can move, which means that if we want to actually explore the universe out there, we need some sort of loophole. And that's what Star Trek did. They were like, well, we're not going to deal with like propulsion and rockets and just moving space or moving ships by using normal acceleration. We're just going to bypass all of that. Now, a lot of people brought up about time dilation and brought up about how, well, yeah, you still have to travel these huge distances, but time doesn't pass that much for you, so it kind of solves it. But it doesn't really. You see, yes, it's true. Time dilation helps the traveler without question, but it doesn't help things like communication or exploration or civilizations. You see, if you travel 100 light years at like 0.99999 times the speed of light, you might only experience a couple of years. But everyone on Earth will experience 100 years. So when you arrive, everyone you know is gone. No one knows if you survived, and any reply that you would send to Earth to say you arrived will take 100 years to get there. So it's not like a practical exploration model. It's it only works if you care. Like, okay, so if you just think about like one-way migration, about using like generation ships just to get somewhere to like leave Earth and never look back, then absolutely sure, fantastic. So time dilation definitely means that like you can travel, and sure, you might experience less time. But if you want to use it as an actual model for exploring the universe and having like a federation, it's just never going to work. So in order to actually talk about warp drive, we have to completely bypass Einstein's special relativity and we have to move into something entirely different, which is why we went into general relativity. Okay, question number 2. It's not really a question, it's more of a statement. I made a video explaining subspace in Star Trek and how that's what they use as warp drive. I got a lot of comments on that video, a lot of people correcting my mistake and explaining that I don't understand what warp drive is and that that's not what Star Trek uses. And that Star Trek actually uses warp drive where it's described as like this warp bubble and it contracts the space in front of the ship and it expands the space behind it. In terms of that video, I have an apology to make. To absolutely nobody. No. Because you're all wrong and I'm right. Subspace existed in Star Trek long before Miguel Alcubierre wrote his metric, which is what you're all referring to. That paper was written in 1994. This book came out in 1991, forward by Gene Roddenberry himself. And Miguel Alcubierre actually is on record as stating that he was inspired by Star Trek, and that's why he wrote his metric, which is a variation or a solution to Einstein's theory of general relativity or Einstein's field equations, and that's what it's described as. Bubble contracts the space in front, expands the space behind. But I would like to turn your attention to page 54 of the TNG technical manual, where it says, and I quote, Cochrane and his team eventually relocated to the Alpha Centauri colonies, a move that took only 4 years because of CDP-powered space vehicles. And they continued to pioneer advances in warp physics that would eventually jump the wall altogether and explore the mysterious realm of subspace that lay on the other side. Now, it goes on to say, during force coupling, the radiated energy makes the necessary transition into subspace, applying an apparent mass reduction effect to the spacecraft. This facilitates the slippage of the spacecraft through the sequencing layers of warp field energy. So when I say Star Trek uses subspace, I have receipts, guys. I get it. We've kind of all Mandela affected ourselves. After Alcubierre wrote that paper and everyone got really excited about like the potentials for actual warp drive being described in physics, everyone kind of just assumed that that's what Star Trek uses. But there's actually a few other things that occur within the show that shows us how they can't actually be using Alcubierre's metric. Even though they do kind of retcon ever so slightly, like as we go on in time, you know, and like new shows, and they try to adhere a bit closer to more modern physics. But still, there's a number of reasons why Star Trek will always need subspace and Star Trek's warp will always need to be different to what Alcubierre's paper was about. Question 3, what are inertial dampeners actually for in Star Trek? So, inertial dampeners exist to counteract inertia. Specifically, it prevents the crew from becoming like paste on the wall or just being like thrown around the place. It allows them to like move and have combat turns and accelerate and decelerate without everyone having to be strapped in. So if you think about The Expanse, right? Every time they need to accelerate the Rocinante and The Expanse, they all have to sit into the chairs because the G-forces as the ship moves forward pushes them back into the chair. Star Trek, they want to be able to move around. They want to be able to go and have a drink with Guinan. They want to be in and out of sickbay, you know? They want to be standing up at the transporters. Like, whatever's going on, they need people to be able to move around. Basically, inertia is the tendency of objects to keep moving the way that they were moving. If the ship moves but the crew doesn't, then the walls will move into the crew, and that's bad. So inertial dampeners are just a storytelling technique to allow the crew to not have to flop all around the place. If we want to get fancy and try to use some technical terms, we can say that it decouples the crew's motion from the hull's motion by manipulating inertial mass or momentum fields and possibly using subspace to reduce effective inertia. Which is, I mean, when they go into subspace, they're reducing the effective mass. So, you know, that kind of makes a bit as close as we can get to like a scientific explanation in terms of Star Trek. But yeah, that is why they have the inertial dampeners. Question number 4. Why isn't the Alcubierre warp drive Star Trek's warp drive? And this comes down to the inertial dampeners. Now, I've already said before, inertial dampeners exist just so that when the ship accelerates, decelerates, or takes any turns, that the crew don't get like smashed into the wall or like flopped all around the place. The thing is, in the Alcubierre metric, the ship never accelerates. Never. The ship sits at rest in its own little bubble. The bubble only moves because space-time itself moves around the bubble. Inside, it is locally flat space-time. There's no g-forces, there's no motion at all. So there's no need for inertial dampeners to protect the crew. But in Star Trek, warp isn't a bubble of flat space-time. It's a partial entry into subspace where the speed limit is different. Now, this means that the ship is moving, it's just in a different domain. It has a velocity in subspace, it's not zero. There's acceleration, there's deceleration. We know this, we see it happening in the show all the time, and that produces inertia, so inertial dampeners are required. So this is another indication that while they may slightly alter how they talk about warp as you get into the later shows to fit more about the concept of actually manipulating space-time, they are still talking about an entirely fictional concept that requires acceleration, deceleration, and requires inertial dampeners to exist while at warp. Question number 5. What does 1 Jupiter's worth of mass energy get you? This comes up all the time, and I understand it. It makes perfect sense. Whenever we talk about like warp drive and actual like physics and papers that have been written to look at like how you could create this sort of a bubble, the common term is always that you need the mass energy equivalent of Jupiter, which is like 2 by 10 to the 27 kilograms, which translates into converts into energy as 10 to the 44 joules. So a lot of people will always ask, well, what does that get you? Like, you know, how far do you go with 1 Jupiter? How many Jupiters do you need? Do you need another Jupiter for a round trip, or will 1 Jupiter just get you to Alpha Centauri, or is it going to get you across the galaxy? The truth is, we have absolutely no idea. There's just no way to talk about this. So what we do know is we're talking about roughly making like a 300-meter bubble. So when you make the bubble, what we don't know is a bunch of other stuff about the parameters. Like we don't know how thick the walls are. We don't know what the effective speed is of the space-time around it, how much contraction or expansion is actually achieved. So we can't really do a direct, like this distance is equal to that energy. You see, none of the models actually give any straightforward answers or like a formula that says like this many Jupiters is equal to this many light years. This is because the models treat bubbles and the distance as like independent things. We just know that it's this much energy to create roughly a 300-meter bubble. But what happens after that, I don't know the answer to. So like what we tend to do is say things like 1 Jupiter's worth of mass energy as a way to like illustrate just how large the challenge is of being able to actually build something like that, or to curve, like how much you would need to be able to curve space-time to create this bubble. But it just doesn't tell you how far you would get. And I know that's not a very satisfying answer, but that's just the truth. Like all of the papers and the work that's been done, that's not really what they've looked at. Just that's where we're at. We're like, okay, make the bubble, but now as to what motion that gives you or where you get with it, we don't know. But if you need 1 Jupiter just to make 1 bubble, you're probably not really repeating the journey too much. Question 6. Can antimatter power a warp drive? This comes up all the time when we talk about how much energy you would need in order to actually power a warp drive, needing like an entire Jupiter-sized planet. People will always think, well, you know, we just use antimatter. And I get so many comments from people saying, just, yeah, that's what we need antimatter for. Now, antimatter converts mass into energy very efficiently. It's one of the most efficient conversions. Absolutely, that is true. But it doesn't solve our energy problem. You see, the warp bubble energy requirement is already quoted in mass energy. So using antimatter doesn't reduce the amount of mass energy needed, because when we say that amount, it's what the conversion of the entire mass of Jupiter would be into energy in a perfect conversion. So in order to create that energy using antimatter, we would still need the mass of Jupiter. It's just half of it would be normal matter and half of it would be antimatter. And the biggest problem really with antimatter is that it's so incredibly rare. Like, it doesn't just exist in the universe in quantities that we can harvest and store. It gets created in very, very small quantities. It's one of the biggest questions in physics, is the imbalance between how much antimatter and matter there is in the universe. We can create it. It is made. It can be made in labs around the world. But like, humanity on the whole has produced nanograms amounts of antimatter in the decades that we've been able to make it, and at a ridiculous energy cost. So it's not really very energy efficient. So when you're talking about like limited resources and having to convert planets worth into energy, it doesn't solve anything. It actually makes it more complicated, because the containment that you need in order to keep antimatter from interacting with normal matter means a huge, massive amount of infrastructure that makes it really complicated. And if you have any containment failure, you're completely screwed. So antimatter doesn't solve our problems, I'm afraid. Question number 7. What do dilithium crystals actually do? I got so many comments about this as well. Again, when we're talking about the energy that you need to create a warp bubble, we're talking about needing a Jupiter. Lots of people said, oh, that's what the dilithium's for. And I think there's just maybe a little misunderstanding about what Star Trek uses dilithium as. And I mean, to be fair, because they do a lot of the time, they're just like, oh, if we don't have dilithium, we can't have warp drive. So it makes sense that people would think dilithium makes warp go. Dilithium actually controls the antimatter reactors. So the warp core runs on matter-antimatter annihilation. That energy has to be regulated in some way, and dilithium acts as like the conduit, the regulator for that, so that the plasma basically doesn't like vaporize the ship. It's not a fuel source or like an amplifier the way like kyber crystals are an amplifier in the Death Star in order to increase the laser output for, you know, super duper planet killer. Yeah, the dilithium crystals in Star Trek are just basically a way to control the flow of the antimatter so that there's safe generation of warp core without big explodey stuff in space. So yeah, so again, dilithium crystals, I mean, I know we're kind of joking about it because like it's obviously not a real thing, but also like it still doesn't help us. Even if we could someday be like, hey, look at this thing, it's not gonna actually increase or help with the energy that you need. You still need the same amount of energy, is what I'm trying to get at, where I'm talking about something very fictional. I question myself sometimes, you guys. Question number 8. Does radiation or heat build up on the inside of the warp bubble? This is something I'd never thought of before. We talk about the radiation accumulation on the outside of the bubble and how dangerous that would be for like when you drop out of warp and all that energy would go forward in like a gamma ray burst. But I never really thought about what's happening on the inside. Now, in terms of the Alcubierre style metric, the inside is flat space-time. So it's local Minkowski space. So everything is like behaving normally. And the thing is, like, infrared heat from people, electronics, all the reactors, everything just has like normal thermal radiation. And that has to go somewhere. So if the bubble wall is like, I'll say opaque, but it's not a color or a material or anything like that, if basically like things can't get outside, then all of that like heat energy isn't going to go anywhere. It can't escape. It can't just emit outwards as normal. It's going to like get stuck on the interior. So you'd be in like a sort of a cavity that's got all this heat accumulating on the inside of the bubble. So at that forward horizon, any light that you emit can't escape. It'll just pile up at the front on the inside of your warp bubble. The quantum field theory on space-time with horizons predicts Hawking-like radiation, which would mean you could end up with like this intense radiation or a gentle glow depending on how long you're in your bubble for. Now, if you're at warp for a few seconds, it's probably going to be fine. It's not going to build up enough to have any effect. But when they're at warp for like days, well, the photons don't have anywhere to go. So all of that heat energy is just gathering at the front of the bubble or on your like forward horizon, meaning that when you do drop warp, as well as your gamma ray burst out, you're going to have some heat coming in at you as well. Unless you can build a ship that is incredibly energy efficient and is able to absorb everything and reuse it or recycle it into the system without letting anything actually emit outwards from the ship. So I feel like that's an engineering problem. Sure, there's one in there somewhere. Question number 9. Would a warp bubble make the ship blind? I can't believe I didn't think about this before. When I was doing the whole series and the long video, I never really thought too much about what was happening with the signals in terms of the warp bubble. But it's so obvious. Radiation can't get in because it's being trapped on the front of the horizon of the ship. Radiation can't get out because it's being trapped on the inside of the bubble on the front forward horizon. No light or signals are crossing your warp bubble, which means you have no communication, you have no navigation, you have nothing. As soon as you actually, engage your warp bubble, you're blind to the universe and you gotta hope everything is where it's supposed to be. So, something that I think is really fascinating that I never really thought about before as well is that basically when you are creating this Alcubierre style warp, the front of the ship that is contracted is essentially a black hole. The back of the ship that's expanded is essentially a white hole. So that basically means that inside the ship you can't detect anything that's in front of the bubble because everything is being trapped in this, sort of fake black hole. Now, it's not that the bubble is blocking anything or stopping anything. It's that the space-time geometry just doesn't allow incoming light to catch up to the ship. So that means that you can't get any communications, but it also means that while you can't see anything, external observers also can't really see into your bubble. So you might be blind, but you're also kind of invisible. So the trade-off may be okay. Question number 10. Could we detect aliens using warp drive? I love this question. It came up quite a lot, actually. So basically what was happening is people were asking if warp drives are possible somewhere out there, then could we actually spot them? And the thing is like, it's kind of going along this idea of like, oh, something will warp space-time and then would we see something weird? But if a ship goes faster than light by contracting and expanding space-time, the light from like behind it or around it might not be disturbed in a way that we would be able to detect because the signal would be overtaken or causally cut off. So basically, if you think about it, like if there's a sun and a ship and then us, and the ship distorts space-time faster than the speed of light, then it's doing it faster than the light from the sun can reach us, right? Which means that depending on as well how far away and how long it's taking that light to travel to us. So, if it's like 50 light years away and they do it like at 25 light years, then it could take, 25 or so years before we would see something happened. We'd be a bit late. But also, I'm trying to get in my head as to whether I think we would even see a change in the light from the sun, So we may see something like indirect, maybe like gravity waves, some distortion, some horizon effects. You know, you could go so far into then like what waist radius technosignatures. We love a technosignature, but they'd be like really, really rare, even if it was a possibility. And it would be something that you'd have to be looking for or know where to look for in order to be able to direct a detector in that direction at the right time and to be able to pick up a signal of a change that happens in space-time at an insanely fast rate. So we know that we can see like changes to space-time. We see, you know, the effects of things like black holes through the light and the way that the light moves around them. So if you have something that's there for a significant amount of time that is distorting space-time, and you knew what the light looked like beforehand, and then something changed, and then suddenly the light went back to normal again, but we'd have to be like focused on that and detecting that for a really long time to be able to collect enough signal to see that there was a change. And even at that, even if we saw the change, there's absolutely no way we would be able to say what it was. It would just be something distorted space-time for a period of time, and then it stopped. What was it? Who knows? We love to say it's aliens, but it's never aliens. Question number 11. Could we surf gravitational waves? This is such a fun question that came up a bunch as well when we were talking about warp drive, because this idea that, you know, we know gravitational waves travel at the speed of light, or like gravity travels at the speed of light, and we know that these waves are big distortions in space-time. So it's easy to imagine this idea of like surfing them. The problem is that any gravitational waves that are like near us are so weak, like incredibly weak. Like even the ones from massive black hole mergers that stretch kilometer scale detectors like LIGO, they only stretch them by tiny amounts. The strains are 10 to the minus 21. Like it's so insignificant. So surfing a gravitational wave, like it kind of implies doing, you know, being carried on it or being accelerated by the wave's motion, but they don't provide a usable wave crest to be able to ride. Not in the way like ocean waves do or plasma waves do. I know a lot about plasma waves. Basically, a gravitational wave is what's referred to as a transverse space-time distortion. They alter distances and times, but they don't push matter, not like the way a wave will push a surfer. They don't have that same kind of interaction with matter. Now, if you were close enough to a source of gravitational waves, so like near binary black holes at a tight orbit, you could probably get like a large amplitude, but if that happened, you would also have like extreme tidal forces and you'd probably be completely destroyed. So building a ship that could actually handle that is, that's no. So yeah, it's incredibly unlikely that we could ever build a ship that would be able to actually surf gravitational waves because they don't move or have like a structure or a mechanism that would be similar to what we understand as normal waves. Question number 12. Could dark energy power a warp drive? This came up a bit on the comments where people saying, you know, how, well, dark energy expands space-time faster than the speed of light. So if we could tap into that, then we could use that to create or to find the source of the energy that we need for the warp drive. Now, the thing is, dark energy, like, it's not a thing. It's just the name that we use for whatever it is that is causing the universe's expansion to accelerate. The point is, we don't know what it is. So people will kind of hear like 70% of the universe's energy is dark energy. That means there's this secret untapped giant power source. But we have to remember that that number includes the vast volumes of space, like the amount of space between all of the things that have like mass that we can see, like galaxies, you know? Locally in space, the actual density or the energy density of dark energy is incredibly small. It's like 10 to the minus 27 kilograms per meter cubed. That's its mass energy equivalent. So even though it's this huge amount in terms of like the cosmic scale, that's because the space between everything is so freaking enormous. So it sounds like there's all of this energy out there, but really just in every small region of space, it's not a huge amount of energy. Now, if you could control it, then you'd be manipulating space-time itself. Sure. And that's kind of the thing that warp drive needs. So it does sound like it's this cool solution, this idea. But we have like zero idea of what it is, of what's causing it, never mind like how to actually like harness it or control it in any sort of way. So it's a really cool concept, and it's a nice idea to think about. There's this energy source out there in the universe, and if we could harness it in some sort of way, and it's already acting on space-time in a way that is causing it to expand, so could we force it to like contract it or something? It's a really fun idea and a fun thing to think about, but we really do have to remember that dark energy right now, it's just a term. It's not implying an actual thing that exists. It's just we don't know what the thing is, so we're going to call it dark because it's dark to us because we don't know what it is. Same with dark matter. We don't know what it is. It's dark to us. You know, that's where we're at with it. And it's cool. It means that there's still loads of stuff out there for us to explore and discover. If you want to think about it in science fiction terms, it's a really cool concept, and you can definitely imagine it in terms of like storytelling and how you could use it. But that doesn't mean that we can actually use it. So who knows what the future will hold.
Scotty, I can't change the laws of physics.
So they're the questions that I picked to talk about, and I hope they were interesting to you. I feel a bit weird about like having done it like this. It definitely doesn't feel as structured as what I would normally do, but I also kind of do like just chatting about it, you know, and I can talk for a very long time. So I should probably stop talking at this point, but I'm sure there are many, many more questions that you would like to have answered or topics that you'd love to chat about. But you can let me know what you think about some of these ones and just some of those ideas as well that, you know, things that I hadn't really thought about. And if I went back now, I'd add them in, you know, the stuff like the radiation accumulation on the inside of the bubble, or the fact that you would be basically invisible to, you know, detectors, but also means you wouldn't be able to get any signals. And there's just so many different aspects to it that, like, I want to be clear, I love it. Like, I love it. I mean, I love Star Trek's warp, which is subspace. No, but I love all these ideas. I love how science fiction can inspire people like Alcubierre to go and like try to find solutions. I love how, you know, this really weird world universe that we live in that has all these bonkers stuff in physics inspires science fiction writers to create crazy stories and explore the bounds of what we know and what might happen and what could be. I absolutely do love it. So I don't want to make my videos to be like, you know I'm destroying people's dreams. But I'm not doing it to do that. I'm not doing it to be kind of like, well, this is never going to work. I'm doing it because I just think it's so interesting. And the thing that I love about science fiction and about science is just that, like, I watch sci-fi and I go, I wonder if that's real. And if you don't think that way, that's cool. You know, you don't have to. Everyone's different. But some people do think that way. And I hope that you're the ones who are here. So yeah. Anyway, I have two things that I can update you on. So the first thing is this video is going to be coming out on Sunday, which will be the 2 weeks after the warp drive came out, which means I will be posting my Patreon video next week, next Sunday. And that video is all about the 3 2021 papers that claimed to have solved some of the energy problems to do with warp drives. So that's the Eric Lentz paper using solitons, the Bobrick and Martyr paper that used subluminal warp bubbles, yeah. And then the Fellin-Heisenberg paper that I think had some other funky geometry tricks. So yeah, and then there's a paper that came out in 2022, which is the Santiago paper, that basically reviewed all of the warp papers and kind of highlighted all of the things or the stuff that hadn't been taken into consideration, and was like, so that is what's going to be on Patreon next Sunday. If you are interested. But if you're not interested in that, that's fine, because the week after we'll be moving on to a brand new topic, and the polls came back and we are doing artificial gravity. And I'm really happy about that, because, listen, I'm not going to lie, when I was putting the first poll up, I randomly, as I was putting it up, for some reason in my head, I'd been thinking about the concept of nothing. And I was thinking about, you know, that episode of Doctor Who, when they're at the edge of nothing, and someone else had like asked a question. There was a bunch of stuff that was making me think, and I was like, that's really interesting. So I added it. And then people started voting for it. And as more people started voting for the concept of nothing, I started to realize, oh, wait a minute. There's not a huge amount of like solid physics I can talk about related to nothing. It's going to be a lot of philosophy. And I was like, this is going to hurt my brain. So I'm not quite ready to go into it yet. So I was really thankful that artificial gravity just pipped it. Like, I mean, I think it was like by 2 votes or something, artificial gravity won. So we will be doing that. I'll be back in 2 weeks' time with the physics of artificial gravity. Thanks for hanging out with me, and I hope that this video wasn't a complete bungly, rambly, incoherent mess. I hope that this works. Maybe I'll be able to polish up the format. We'll see. We'll see how it goes for a while. And if you like this, if you like me doing it like this, then I will do more of them. Or like I'll do one every month for whatever the main video is. So next month, artificial gravity. Cool. Thanks for watching. Stay nerdy.